The files for this class are online. Slides are online, Moodle right now. And today we're talking about exploit mitigations. Okay, this is the lecture where I get to tell you everything we've learned so far no longer works. Right? Everything we've done the first half of the semester is kind of useless, but that's a good thing. So just real quick, project 2 is ongoing, due after break, I believe, the Tuesday after. Next lecture is going to be a lab where we do ROP hands-on, talking about some of the stuff that we learned in this class, the ROP stuff we've learned previously, and then we have an advanced ROP class also next week, and then group assignments today. Any questions on any of that? Project, class logistics?
I'm taking this as after.
After spring break. But no answering campus-wide, guaranteed.
Okay.
So if you have questions, get them soon. Okay. So just quick recap of what we did last class. Last class, we only talked format strings, how you can do memory leaks, writes, different things like that. We kind of learned how dynamic compilation works, right? So if we dynamically compile a program, we need to access things in like libc. And the way we do that is with a table that is constantly updated throughout the execution of the program. Last year, we went a little bit more in depth on how this worked, and it seemed to confuse people, so we kind of waved away all the details. So all you really need to know is that the global offset table, for now, is a table of offsets of memory, where libc functions are. And after you call a function for the first time, it's populated by a dynamic linker. And maybe if you can read and write to that table, we can jump to other things and in memory. So it's kind of interesting. It's a tool that we'll learn for exploits this lecture and next week. Okay, so just high level, global offset table has dynamic linker info, function offsets for libc, load into memory during runtime. Again, we don't do it at the start because that can be very time consuming, resource intensive. Say I don't know, what's a common program that's run a lot? Schedulers, like thread schedulers, right? That's probably some process relating to that. That's called very often. Imagine if every possible code branch of that program always had to be loaded for all their like libc links, right? Every time. And maybe you only use one libc function every call, right? That can get very time consuming and hang your kernel. And then the procedures linkage table, it's actually what we would call when we want to do calls to libc functions. We call it PLT. And the PLT then redirects us to the global offset table. Remember that PLT doesn't actually store any function idea or function information besides offsets into the GOT. And everything's populated after the first call, right? If we haven't called a function, then we don't know where it is yet. We have to call it first, and then the dynamic linker will tell us. So let's talk about exploiting these two tables real quick. So if we want to call a libc function, we need to know where it is in memory, right? So something that we can do, because we know where the global offset table is, it's part of a user-defined process, so it's loaded in a fixed place in memory for now. We can just leak that memory address, right? We use printf in format string exploits to leak stack memory, and there's no real reason why we can't do that with global offset tables, right? Maybe we can't do stack pointers, but maybe we can do a %s, leak it as a string, and then give it the address of the global offset table, right? So that's ways that we can get random memory leaks that aren't stack-based, and this will leak us actual addresses of libc functions, right? And keep in mind, libc is one continuous block. If I go to my VM and I run, I think this one, and we run it, and then we run VM map, we can see the executable part of libc is all one continuous region in red, right? It's not split up. So if we know where one function is, every other function is going to be in that same rough memory region, okay? So one leak gives us basically the entire library to work with. Okay, and then consider if we can call GOT, I make this bigger, and we have access to like the global offset table. We know like puts is in our global offset table. It hasn't been populated yet, but once it is populated, we can just overwrite this access if we have writes with format strings or whatever, and some other bug. And then next time puts is called, it'll jump to whatever we write it to instead of the libc function. So we can actually use the global offset table to get arbitrary code execution. Okay. Any questions on this? Okay, we haven't demoed it at all, but that'll probably be in the lab next week, where we have like a guided walkthrough. It's kind of a little bit troublesome to do live coding sometimes. With the format string writes from last lecture, I posted the code in the CampusWire thing. I can upload the file too. But I wrote the exact same code and it wasn't working for some reason and no idea why. Okay, so yeah. And we can just, if we want to overwrite GOT, it doesn't have to be to another libc function. It can be shellcode to a buffer if we have a pointer to that. But usually, so now consider the case, right, where is the eraser? We have GOT, right? Okay, so we can write to the global offset table, and we have a buffer pointer, right? Previously, if we wanted to get to our shellcode, we need to also overwrite the return address, right? So we need to overwrite the return address, set the return address to the start of our buffer. With GOT overwrites, we don't necessarily have to overwrite the return address. So if we have the GOT as like a database, right? And we say like puts is here, gets, maybe you also have like fgets if the program's bad, and you have both of these, right? Let me get a better marker. So what we can do is in the puts address, do our buffer pointer, right? We can overwrite this instead of, usually it's like 0x7FFF something, right? Some libc address. So then next time we call puts, it goes to our buffer and our shellcode without overwriting main. So if we look at exploits later on and some mitigations, it's actually pretty important that, sometimes we won't be able to overwrite the return address. Okay, attacks and mitigations. So why do we have mitigations? Why do we need them? The general concept is getting hacked sucks, okay? You see in the news, there's always companies getting ransomware. The government's always looking for hacks. Like, it's just a general bad thing to get hacked, right? I feel like that's pretty obvious, but the reason we make mitigations is because we want to stop this. A lot of the times we have pretty simple tools to stop a lot of the bugs we're talking about. We've mentioned some in class already, but we'll go over it again. All right, like usually these are pretty trivial things to implement. The problem is just we haven't implemented them or we didn't think about the exploit. So we just it's a little too late. And then you have to consider writing good code is very hard, okay? Everyone's 230 code probably is very bad. How many times did GCC yell at you and you just ignored the warnings? There's good reasons the warnings are there. And then if you go to the corporate world and you're working on a million-line project, it's not your problem to fix all the warnings, right? If other people are making pull requests every day, guaranteed whoever's looking at this pull request says, looks good to me, and hit submit, right? That's just what the real world's like. And there's answers, people are trying to make answers to this now, like something that we used to joke about every class last year was just write Rust, right? Just rewrite everything in Rust, problem solve. But that's also is not viable, okay? The switching cost of making all your developers learn Rust, where they're probably going to go run things inefficiently because they don't know how to use the programming language. And then a lot of the libraries you're going to want to use aren't ported in Rust yet, so you can't use them. It's just insane switching costs. And then, because Rust guarantees safety through compilation, right? It does all your memory checks for you, make sure you write good code. If you're doing a million-line project, your compilation times could 10 times, right? So, who here has done DevOps stuff? Anyone? Okay, only Sergio. But you don't really do DevOps, you just do server hosting. You haven't run who knows what Jenkins is, right? Okay, a few people know what Jenkins is. So Jenkins is a system where you can hook it up to your projects. It'll automatically build and distribute stuff, right? And what you can do is you can put test cases in it, and you can do all these different things to make sure your project's working from every pull request and you get the latest version. Now, when people say there's a nightly Jenkins build, right? Usually as developers, we view nightly as like experimental builds. The reason we use the term nightly is because compilations will run overnight. These things take like 10 hours. You put it on when you leave work and you wake up and hope it works. And if it doesn't do that, you wait until the next day, okay? So if that's with a C++ project, running all those tests, all your build times, now do it in Rust. If your compilation takes 2 days, you're paying someone the extra 24 hours to do nothing, right? So you really have to consider that from a business standpoint. And then like, people won't want to learn Rust. This whole makes so many problems. And then also, besides that, just from implementing security checks, so that's like writing good code, right? But then there's always going to be some bugs, even in systems. So if I'm writing a program, there's always going to be operating system bugs, no matter if I write good programs and use them, right? So I'm still screwed no matter what. And then there's hardware bugs. So there's always going to be bugs, so you have to write mitigations to stop whatever exploits you don't know about. But then, we could write the securest operating system in the world, but could do one operation a second, maybe, right? It would be insanely slow. So something we could do is think about every exploit we've done in class. We could literally check every single memory request and every single instruction with some arbitrary mitigation check and just stop all exploits. But you know what? No program will run in efficient time and no one will want to use your computer. It'll be like going back 20 years, okay? So that's why it's a trade-off. But still, there are general things that we can implement that are efficient and stop a good amount of bugs, right? Any questions on this theory, viewpoint? Does anyone want incidents? One thing I used to like is this. Okay, I will not name what branch of the military did this, or what organization it was, but there used to be an organization that would run outdated versions of their services on purpose because they would always forget passwords. They didn't have like good IT systems. So every time they forgot their passwords or got locked out systems, they would just run kernel exploits against their own systems to get back into it. And this was just something they did for years until a bigger agency bought them out and it was like, Jesus Christ, this is like Snowden waiting to happen again. So you'll be quite surprised how bad things are in the real world. Okay, so let's actually get into it. Buffer overflows. Easiest thing we learned it like week 1. What can we do with it? We can change local variables. We can redirect execution. We can write our own code and redirect to our own code. How do we stop this? Any ideas? Greg.
Mark this stack as like non-executable.
Okay, so we talked about non-executable. That's one idea. Now, what does that solve?
When you jump back to your start of your buffer to execute your shell code, it won't like actually execute code.
Right, so it stops us from executing our own code. What does that not solve?
Overwriting stack variables.
Right, and?
The return address.
Yes. Okay, so ROP still works. Oh no, still screwed. And I argue that changing local variables is still insanely bad. So if we have any password checks that has a 0 or 1 flag and we just flip it, still screwed. Okay, any other ideas? Think about it. Okay, so yeah.
Randomized address system memory.
That doesn't really help right now.
Oh, okay.
Too far ahead. Okay, so we solved the shellcode issue by marking the stack as not executable. What is a way we can stop overflowing local variables? Yeah.
If you like get the amount of bytes read in, then you could just compare that to the size of the buffer.
Okay, so we just do buffer checks, right? But that like boils down to not using the gets function call, and guarantee people here have used that. So that's like a use Rush issue, right? Just program in Rust. But assuming you're not programming in Rust, what's a compiler thing we can do to make sure this isn't a problem?
Put the buffers at the top so that it can't go into variables above it.
Yes. Okay, so we can put the buffer at the top, right? Every other local variable is below it. Maybe the data is saved, but what if you have 2 buffers and both of them are bad? Still screwed. But that's an edge case, right? That's a good idea. Compiler has done that. We've seen it. So If you put on the right flags, that's not a check. Any other ideas? Yeah.
Stack cookies?
Okay, yeah, we'll get into that. That's a good one. That's basically what I was looking for. So,
Wait, is that the same thing as stack canner?
canaries, yeah. So the first one is executable. Formally in industry, this is called DEP or NX based off the operating system, which is execution prevention or no execute, which basically is just give every region in memory its own flags, right? So if we run VM map on a program that's going, like I've shown a few times, anything in red is executable, and then like yellow is stack memory. You can see all these different things are different things loaded, and these are like decided by the kernel kind of. But you can see here, we actually have flags for read, write, executable. So you can see the only thing that's marked with an X is stuff that we should deem as code. So our program code, libc code, and a dynamic linker code. So and you can see the stack is readable, writable, but not executable. So that's an easy fix. Instantly takes out any shellcode in user. Okay, huge exploit, gone. This does not solve ROP though, because ROP reuses code in the executable section. So keep that in mind. Do I have any other things? Right, like in generally the principle behind this is any variable should not be executable. So where we have globals, not executable. Heap data should not be executable. It should make sense, right? All of this should make sense from like general like logical standpoint, right? And like the overhead for implementing this is very easy. It's one extra bit check for all your pages and all your memory locations, right? So when we say we have a 64-bit CPU, generally we only have 48 bits of available memory because those 16 bits give us different flags.
It happens anyways, like the memory check, it's mostly just like a compiler flag.
Yeah, it is a compiler flag.
I expect the CPU does the check anyway, so it's like no extra cost.
Yeah, so that's what I'm saying. Like, right, like all these bit checks is based on like the actual page table structure, which is part kernel, part CPU. So your hardware is generally very good at doing this. And if you try to execute memory that is not executable, it'll do a hardware page fault and not a kernel bug, right? So it's very fast. This is very easy to implement. Hardware has been specialized to do these types of bugs, bug catching. Okay, so this stops shellcode. There's still other bugs we talked about, like changing local variables and redirecting execution. So let's look at a fix. Anyone? One more check before I give the answer. Any possible solutions? People said it, but I don't want you spoiling it yet. I want someone to come up with a theory. They know it already. Yeah.
Make a variable check that if the variable gets changed, then you like crash or you exit.
Okay, but how do you tell if the variable was supposed to change naturally in the program?
It would have to be a variable that's like not supposed to ever change, like something that is just the check.
Yep. Okay. Okay. I guess it's the next slide. But reordering the stack, right? If there's multiple buffers, you get screwed. This generally stops us from ordering local variables, but return address is still bad because return address is always going to be on top. There have been papers, I don't know if anyone has implemented this, which wanted to keep two separate stacks, one for just local variables, where you still have the base pointer information for every function, but all stack information relating to execution would be a separate place, so any buffer overflows wouldn't mess around with execution. But I don't know anyone that's implemented that. Do you?
It's like just keep.
Yeah, like all like return addresses would be a separate memory location.
Just not the von Neumann architecture. It's the thing we had on the first day of class, the different memory architectures.
Oh yeah, but that's lame.
It's like embedded devices really good fit, but yeah.
Yeah, if it's not x86, I don't care. Okay, so stack canary, stack cookies. Both these people mentioned it, and you basically had the theory. So what we add, the name, first of all, let me say the name comes from miners used to bring canary birds down with them in the coal mines, because if there's toxic gas, I think the birds would either chirp or go quiet, is one of the two, and there's a way to tell before humans could if you're going to die from gas, right? So the idea is we add a dummy variable to the stack, and let me show you where on the stack it is. So if we have our stack going down, like usual. And the return address is here. And then the base pointer is here. Then the canary is always right here, right before the base pointer, because we want to detect if we corrupt anything relating to function data, right? And then our buffer would always be below it. So all local variables are below the canary. So basically, what we do is we set this value, we do all our normal function data, and right before we return, we check if this value has changed at all. And the way we check if it changes is the canary is set to like a side register that isn't really used to anything else. So the check is always safe, right? It's not like we check it against another variable in the stack, which could also corrupt. And if this variable's changed at all, then we know there's been an overflow, and your computer will crash. Or not the computer, but the program, right?
If you have two buffers, would you use two canaries or just one above both?
I have seen, not x86, but I have seen things implement a canary per buffer. I think it's fine. I think it might be a little unnecessary, because generally, if you have two buffer overflows, you're screwed no matter what. Yeah. This is mostly stopping execution jumping, right? This is not a fix for overriding local variables, because if you have another local variable right below the canary, you can still corrupt it, right? Canaries just check for program execution changes. But then you say, like, if your buffer's on the top because your compiler optimized that, then maybe you are safe, right? Maybe if we implement enough of these mitigations, it just makes the attacker's life hard enough where they quit.
Yeah.
And, like, to be fair, that is what people do. Like, most of the defense side right now, I mean, you can patch all the bugs you want, there's always going to be more bugs, but we can just make it hard enough where the government's not going to pay, $10 billion to find a really bad bug and exploit it. If we can raise the cost to $100 billion, then that'll take a lot of people out of the business.
When you're looking at like modern hardened targets like browsers, kernels, whatever, especially browsers, oftentimes like fully going from finding a bug to developing an exploit takes an entire security team at least a month, oftentimes. And that's like paying a team of senior security engineers that make like $300,000 a year, usually, like paying them, all of them, for like a few months for that one exploit. It's like it gets really expensive with all these mitigations. They make things really hard, and yeah.
Yeah, I mean, to put it in perspective, how much people like put into the actual exploitation part. My boss found a bug incrementing a struct counter. Right, I feel like I talked about this before. Where the struct counter would overflow after like 3 million, but that would take so much memory and so much time to allocate all that it wasn't usable. So they paid people, hundreds of thousands for months worth of work to investigate memory compression so they could get that bug to be exploitable, right? So it's like a complete other part of the kernel, seeing if we can figure out and abuse that so we can make this one little overflow bug work. And then you don't know if that's even exploitable past that. It's just if we can trigger it, right? So the level things have gotten to is like really insane in terms of like costs outweighing benefits. Okay, so the canary, fun fact, the first byte of it is always a null byte, right? It's always going to be 0, 0. And the reasoning for this is, think about printf, right? If there's a printf bug and we can print strings out, right? We can control whatever string we print. Maybe we can interpret the canary as a string and print it out on a stack, right? And so we can do pointer leaks all we want, but say the program's actually good, right? Say the program isn't that bad. So it has printf %s, right? It prints a string, and it's not a straight bug. We don't control all of it, but it takes a buffer, right? So this is how we normally do it. But if our buffer is completely full, all A's, right? All the way to the top, printf only stops string printing when there's a null byte, okay? So if we continue all this way buffer and we never put a null byte in our input, or we just like say this buffer is 64 bytes and we fill up all of 64, like usually we do end-line parsing and you make sure there's no off by ones. This stops an off by one error because it'll always stop interpreting the canary as a string right before you read its value, okay? Now what you can do is if it's a gets, you can overwrite this null byte and then read the rest of the canary, and you know the first byte's always in the play. So let's actually look at that. So if you want to look at the, I think it's stack something is the program. Okay, so we have the stack demo.c function, right? All this is a buffer of 8 bytes. It prints a pointer to the buffer, and then it calls gets, right? So this is a function that we've basically worked with all the time. What's the exploit here? Yeah.
We have gets, and we also have the memory address of the buffer so we could execute shellcode.
Yep. So we can do shellcode. We can do code redaction. There's not really enough space or interesting things to do what we want, but general the concept there of the vulnerability. So what I gave you is all these different GCC compilation flags, right? The first one is no protections. The second one is no canary, and the first one is default all protections. So if we rewind history a bit, the first one is what the default was maybe, I don't know, 20 years ago, 15 years ago. So let's compile that. And then I also gave you stackdemo.py, which is just Python code that does the buffer overflow and redirects to the buffer, right? So all we're doing is seeing if we can actually trigger the return address to go back to the buffer. Okay? We're not doing any exploitation. We're just seeing how mitigations stop our usual techniques. So let's run the stack demo with all the mitigations turned off, right? We're in GDB. I'm just going to disassemble main and break at main plus 59. So right before it returns. So all the Python code does, if you look at it on your screen, is give 16 bytes of null opcodes, which do nothing. It's just to see if we jump there, and overwrites the return address to the buffer. So if I continue to the return address with no mitigations enabled, what should we see? Yeah.
The return address is like overwritten. Wait, if you have no mitigations.
Yeah, no mitigations. Right.
Yeah.
Okay, it'll be overridden to the buffer, right? And we should be able to see the NOP shellcodes we did, right? So let's hit continue, and we can see right before we return, the function is ready to jump to our buffer, okay? This is what we normally do in class so far. Okay, nothing has changed. So let's exit out this. Clear, we'll cat stack demo again. And now we're going to put these flags. So let me first explain flags. So F no stack protector, this handles reordering local variables. So your buffer's on top, and this also puts the canary. So basically, basic stack protections, right? That's what it stands for. And F no is not putting stack protections. Z exec stack is your what's it called? NX step mitigation, so making the stack not executable. And then no PIE is one we haven't talked about yet. So also, I think I have it installed. I can't type today. Do I? Yeah, okay. So I think if you install Pwn debug, it should also come with this command checksec, which just basically prints what mitigations are enabled on a binary, right? So if I go back and I do the no protections flag, and then I run it again, I didn't do the no protections one. Okay, we can see nothing's enabled, right? It's all red. And you can see stack, no canary found, not executable, disabled. So this is a good way to check what the binaries actually have enabled. I recommend doing this for the next project because project 3 will have mitigations in some of the binaries, right? So you're going to bypass these stuff. So if I look back at the stack demo, and now we just do no canary, right? We run checksec again, right? We now see not executable is enabled. That's the only change. Okay, let's run our Python script again and see what changes in the exploit. Any predictions? What changes? what should we see? Right, the only change is we made it so the stack's not executable. What should we see? Should the buffer overflow work?
No.
Well, just the overflow part, should it work?
Oh, yeah. Yeah.
Okay, so we can write the bytes. Can we overwrite return address?
Yes.
Yeah. Yes. Will jumping to the buffer work? Can we jump to the buffer?
No.
No, can we just jump to the buffer?
Yes.
Will we execute it?
No.
No. Okay, so let me disassemble main again, break at the end. And we can see we're about to jump it, so I'll just do a single step. And all that did was execute the ret, so now we're at the start of the buffer. I'll do another step. And you can see we didn't move from the first now. I keep doing it. Nothing happens. And you can see we got a seg fault, right? So this is the actual operating system stopping us from executing this code. Right? So this is the effect of no executable. Our shell code no longer works. Yeah.
Did you still use this exploit as like a denial of service when it crashed the program?
Yeah. If you want to crash something, this is a perfectly fine way to do it. Okay. So that's bad for us as attackers, but good for the general world. Okay, and we're going to compile one more time with stack protectors on, right? We'll run the Python code one more time. Okay, now we should be able to see the canary. I'm going to break in main. I didn't do that. I'm going to break at the leave, so actually I want to break probably at the fget, so we'll do plus 66, right? We can already, this is because, what's it called? The GDB attached late. Can I see it here? Okay, we'll just run it again. So we'll break. So what we can see actually in this assembly is, remember I said the canary gets it from a weird register, so we can't corrupt the actual check. That's what this FS is. So you probably saw in Ghidra doing like project 1, maybe like some weird stack check function with like some FS register in your disassembly. That's what this is. Okay. So whenever you see something like FS offset, this is a canary value. So we'll break like main plus 25. This should be right after canary's set. We'll run the program, and we break. And let's look at the actual memory of the program, right? So this is the top of the stack. Base pointer is here. This is the return address. As you can see, it's going to libc start call main. So what should this be?
The canary.
Yeah, right. So it's after a buffer before the base pointer. Like we talked, it should be like right here, basically on the stack. And we can see that the first byte's actually null, like we were talking about. Okay. If I run it again, and we see the canary value change, but the last byte's always going to be null. So I'm just going to run it one more time. You can see this value is always changing, but the last byte's null. Okay. And like we said, that's for potential printf bugs like that. The last byte. But you can see if we continue our buffer overflow. So let me disassemble main and break right after it gets. Okay. Put a bunch of A's in. Okay. We can see now that the stack is overridden. What is it, like 32? Something like that. There's no like null byte. How do I view in hex? Something like this. Yeah. Okay. We overwrite a bunch of things, and this should crash, right? And we can see we're getting it'll even tell us stack smashing detected, right? You probably saw this in 230 a lot. So we know this is from the canary being overridden because it detected a buffer overflow. And usually when it does this, you don't get a normal seg fault, you get like a forced thread kill because the kernel thinks it's malicious. Okay. Any questions on canaries buffer overflow defenses? Yep.
How is the canary generated? Is it like randomly like seeding the system clock or something, or is it like in any way predictable?
Gilbert, do you know how canaries generated?
I know where it's stored, but not how it's generated.
I think it literally, because okay, the general way to do random bytes is like you random, right? But it's not you random.
It's probably just the OS use one of its random functions when it initializes the process. It writes the canary to like the memory region that it's expected to. So just like initialize at the operating system by using some randomness mechanism.
I think though it just grabs some bytes from a random. So I think the FS register is deemed random enough. Like it'll just be pointing to random data, and it'll just grab whatever FS is pointing to at that time.
I don't think so.
Okay, we'll look it up. But I've seen implementations like that where they use like a segment register that's really not initialized, and they just take
FS is initialized though.
We'll see. Okay. So how can we bypass this? Yeah.
Is it the same canary for every function, or is it different?
I think it's the same, right? Because you expect if you find a canary that's broken, right, you should quit. So you should never need a different value, because if you already have one leaked, you should be able to detect it in the first place. Okay. So what are ways you can bypass these mechanisms? Yeah.
I mean, if you figure out the canary's value, you can overwrite it with itself.
Yep. How would we find a canary's value?
Like a memory leak.
Okay, so we can use printf. That's the canary. How can we bypass no executable?
Use it all.
Yeah, we can use ROP. What was the other one? There's one more. Or order on the stack. Maybe we can't change local variables. That's the one thing we kind of lose out on if things are ordered well. So it's just what we said, right? So bypassing the executable, we could just use ROP and reuse existing code. Something that we can do, and I think you may have to know in theory for project or midterm, so keep this in mind, that we can use, if we can do ROP, we can create our own executable zones in memory using mprotect as a syscall, right? There's actually syscalls that will allocate memory locations, and we can set those to read, write, executable, and then push out code there. Okay, so keep that in mind. Bypassing stack canaries, printf is usually your go-to way of doing it. So maybe you find a memory leak bug that you can take advantage of. You get the canary value, and then during program execution, you change your payload live to inject that canary value during the buffer overflow. So something we can actually do. I say we have our buffer overflow. We already leaked the canary. We can write in the second pass, so say we already have the memory leak and it's waiting for more input, we can do our shell code and then continue the buffer overflow to now overwrite the canary, but instead of overwriting it with just A's, we just rewrite the actual value of the canary, right? So it never gets modified. But our buffer overflow then will continue into the base pointer and return actions. Okay? So keep in mind that a leak and a buffer overflow still gives us full ROP, like usual. And maybe even shellcode with no executables on. And then, maybe you don't need to do a buffer overflow. Sometimes like out of bound errors. So like if we're having a function that writes to an array, but there's an out of bounds access to that array, we can jump over the canary and do writes or different things. You can be creative with it. So let's talk about the best attack we could possibly do theoretically with all these enabled. Threat to libc, right? When we're doing shell coding, jumping to another function is generally considered threat to win. Jumping to shell code is threat to shell code. This is threat to libc. So we find a buffer overflow we want to use, but all mitigations are on, so we can't do shell code. There's going to be a stack canary, so we need to find a way to leak it through printf or whatever. Then, if we find enough gadgets, we can do things like call system through like syscalls, right? Maybe you can execute binsh like we've been doing already in class. But realize that now we need 2-3 components of everything. We need a leak, we need an overflow, and we need all these gadgets to be in the program. And generally through system, or if there's already other functions, so maybe our program already calls system, that will be in the program somewhere for us to recall again, or it'll be in the GOT. So maybe we can just leak the value, or we know where the GOT is in memory, the actual table itself, so we can just jump to the GOT with the right parameters, right? So, we can do this exploit that we've been doing, but now that mitigations are enabled, we need 3 more facts of information, okay? Again, our life's already getting hard, but this is what industry's like. Okay. Any questions with regard to libc? Okay, let's go get harder. So now we're entering the point of mitigation where generally it's around randomization, right? So we have a lot of things taken for granted right now. We know where the program is in memory, right? All our ROP uses consistent locations in memory. Very helpful, very bad for security, okay? So we'll look into what happens when you randomize that. ROP, a little harder than buffer overflow technically, but it's actually usually easier to execute if mitigations are off. Buffer overflows, you need, pointers to buffers. ROP you don't, right? So it takes less memory lanes. What can we do to stop this step? The first one is ASLR, okay? Address space layout randomization. This randomizes the location of everything. So stack, heap, program code is no longer at the same 0x4000 or 40,000, right? Your program code will now get loaded randomly in memory. And libc functions, libc will get loaded in random locations. ASLR is usually on by default now. I guarantee you, all of your operating systems right now are running ASLR. If you want to turn ASLR off, you have to change it can you even change it in boot settings, or is it recompile ASLR?
You can turn it off in OS settings.
Okay, so you have to change it off in your kernel settings and then reboot, right? This isn't something you can just abuse from user hard. I don't know if we mentioned PIE, but PIE stands for Position Independent Execution, right? So for our code to work anywhere in memory, we can no longer use hard-coded offsets for functions, right? So currently, if we have main, right, we have our main program, and it wants to call function 1. The corresponding assembly will be call func1, right? And if you look at the actual opcode, this will be 0x4000 something, right? We can't do this anymore. Because if our program's loaded somewhere randomly in memory, this value's going to change. Okay, so what we do, we now change it to call func1 goes to instruction pointer plus some offset. So this offset could be ABC bytes, right? So now everything in our program is written relatively to where the calls are, to where main is basically the base of the program. Everything's written in relative regard to the base of the program. Okay? So this is basically how we call libc too, right? So think about if we want to call libc, the dynamic linker tells us where it is in memory, and then we're calling offsets of functions basically. Okay. Yeah.
So given that we have randomized everything, wouldn't that slow down the general, the execution, wouldn't that also slow down? Because now we're making it hard for both for the gadget to find it and also for the code, or is it?
No, so all these offsets are calculated during compilation time. Okay? So once we compile, it's fine. This can be loaded anywhere in memory. And then ASLR is not a performance hit because we're already doing virtualization, right? So normally, everything before this lecture, everything's loaded in one location, right? But that's because everything's loaded in one location, nothing's actually loaded there. The operating system says, hey, you're accessing memory location 40,000, but in reality, your program's here and does all the offsets for you. Same thing goes on in ASLR, right? So it's not really a performance hit at all. This is why this is a good security policy, right? No performance hit, only good security. Any questions about ASLR? Yeah.
Well, you said it's all offsets from the base of the program, so main. So can you use?
So, well, actually, it's not main, but yes.
Or it's the
Yeah.
start or entry function.
Yeah.
But if you can find that, then can you just use that offset?
So let's think about this. Previously, if we wanted to jump a function, we just look in the code and say it's at this location in the program, right? Sounds pretty easy. Now, if we want to jump, say we have some exploit and we want to jump to function 1 from a buffer overflow main, we have to find a leak of where our program is in memory now. So it's another leak. So I think it's on the next slide. So this is basically how you bypass ASLR. We have some buffer overflow. somewhere in the function, and we have some function that can print. So we have like printf puts. What we do is we pass the address of main or some function to these print functions, and we get them to print the address of somewhere in the code, right? And if we know one set location in the code, then we know all the offsets, right? And there's actually ways to do this in point tools. So let me see. I think it's puts.py. I think it's this one, right? So in this, you can see I have this line main address where I'll talk about how we leak it later on, but we actually calculate the base address of the program by subtracting the symbol main from the main address we get from the leak, right? So let's just go through this one exploit. So what we have for this exploit is ASLR enabled dynamic linking. So it calls some functions. We have a buffer overflow. So first, buffer overflow, right? And we will just assume ROP because stack stuff is enabled, right? So we have the GOT and PLT. So let's call a print function of puts, right? Call puts. And then, so assuming that we can call puts, right? We need something malicious. So assume we can control the variable to puts. What would be something interesting to pass to puts? It says it on the screen. Yeah.
The GOT entry?
Yeah. So this is like assuming we have some leaks about where something is in memory, right? So if we call, so say we have a printf and we can leak all the stack, right? Say we can leak the location of a function from the stack. Then we can pass that to puts and have puts print that location, okay? So let's look at the ROP puts.c program, right? So you can see this calls puts, and we get a print %p to main. Okay, this is all we're given is a pointer to main in the buffer overflow. So with this pointer to main, we know where the program's loaded in memory, right? So we know from Ghidra or any other tool like object dumped, we know where main is in the offset of our code, right? Maybe it's like 1,000 bytes down. So we can then, from this main pointer, subtract how far down main is, and we get the base of our program, right? And we can see this reflected in the exploit code I gave you guys, so ROP_puts.py. So we're going to get a main address and a base address, right? And then from there, we know exactly where our program is. If we know the base address, we know where our program is loaded from ASLR. It's some random location, but now we can calculate everything based off offsets with symbols, whether we find that in Ghidra. Pwn tools has a bunch of things where you can just do dot symbols and toss a name, and it'll give you the address, the offset, sorry. So then we have offsets to main, we have offsets to all gadgets if we have the base, we have offsets to the global offset table, right? So we have a bunch of stuff. But now what if we want to call libc after getting the leak of where our program is, right? So that's the question. So if we have, I'm going to look for that marker again. Hopefully this works there. All these markers suck. So we know where our program is. So we know where the global offset table is, right? So we can then pass the address of the global offset table to any print function. Okay? So now we can print the global offset table. Does this make sense? And from printing the global offset table, what do we get?
Yeah, address of empty.
Of what?
Of libc function.
Right? We get address of libc function. And we can do this through puts if we pass it the right parameter. We can do this through printf if we pass it the right parameter. So say we want a specific libc function that's not used in our code. How can we do that? Yep.
Use the offset and then based off the version of libc, you check it and then you call the offset of the function you want with respect to the function you have.
Yeah. So you may ask, like, how the hell do we do that, right? It's convenient when we have the actual binary. We can use like Pwn tools, like in a script, to print the symbols for us. We can calculate the offsets like that. You still need a leak somewhere, but you have the offsets. Well, libc seems much bigger, much harder. You don't have the source code. Digging through Ghidra might be a pain in the ass. So let's GDB rock puts, and I'll show you something cool. So I go break main, run it, disassemble main, does a bunch of things. I don't really care. I'm going to break right at main plus 57 because I just want functions to be called real quick. Okay, that's the only thing I'm doing. I just want the GOT to be populated. We have some values. So this is where things get fun. So I'm going to pull up this website called libc database. Can anyone guess what this does? Yeah.
Basically contains, it's a database containing all the known versions of libc.
Yes. Okay, so what we're going to do is we see this is the puts function, and it's this value. So we're going to say, if my Firefox unfreezes, give it a second. I really need to switch to Chrome. This happens way too much. Okay, so we'll write puts here, put that there, and then we're going to get another one. So print f, we'll just copy this value over.
Wait, it needs 2?
Yeah, because you need 2 to tell the relative. So if we knew the libc version, we would only know 1.
Oh, okay.
Right? But if we don't know libc, then we give it 2 symbols, right? We hit find, and it tells me the exact libc I'm using based off the known offsets between these 2 functions, right? Because every libc is going to be slightly different. And if you have collisions, maybe you just pass it a third symbol, right? And every time you compile, it'll be slightly different. So just from leaking global offset tables, right, I know exactly the libc version I'm using. Because I know 2 functions that are just in my program's memory. And now I know the offsets of those 2 functions. I can calculate the libc just from a lookup table. And now that I know the version of the libc we're using, I can download it, put it in Pwn Tools, have it calculate offsets for me, and I know exactly where the function system is. And I can just call system now, right? So you can see, just from knowing where our program is in memory, we can leak libc, assuming we have enough leaks in the code. And we can start just calling any libc function. Okay? So ASLR pain makes it so we need a lot of leaks, but it still can be bypassed. Any questions for that? This is a lot of theory today.
This is only because we also have symbols not stripped from the program as well, right?
For what? What do we need symbols for? Oh, in the reversing?
Yeah.
Yeah. So this is assuming that you have the program yourself to find offsets. You know, it's generally very hard to blind find bugs in the program. But usually you have an open source tool and you're compiling it. Like, if you're doing Windows stuff, you have the Windows operating system. If you do any open source Git tool, you can compile it yourself and get these offsets. It's really just a problem to find where, what compiler they're using in that instance. Or like, like, hey, this function calls this function, right? Even if function 1 calls function 2, even if I don't know what compiler they're using, if I can leak the addresses of both, then I can still get some offsets, right? And then you play the same game like libc. Any other questions? Yeah.
When I was running this on my own virtual machine and put the 2 addresses in, I got like 10 results that all look very similar, but they weren't more than 1.
What operating system are you running? Does not sound like Ubuntu.
Right.
That would do it, yeah. So now you need more, you probably will need more leaks, right? So the game you play now is get more leaks from global offset table, keep plugging them in, or you just brute force. You know, if there's only 6 libcs, maybe you download them all and you run the exploit 6 times and you can win that way. But yeah. Okay. So this is a general way to bypass ASLR, right? You just keep getting leaks. You play your game with ROP. You try to leak your function or your program. Eventually, you try to leak the libc program through global offset table. You just keep playing this game, right? Leaks, find out information, exploit based off that information. Kind of like a game. It's a puzzle, right? Any other questions before next slide? So, going off PIE, I don't know why I didn't put this slide before. Is this exactly what I just said? I think it is, right? ASLR randomizes the location of everything. PIE just makes it so our code can run anywhere, right? They kind of go hand in hand. PIE does nothing if you don't randomize it. You can technically have PIE and still put the code in the same location every time. It'll still work, but you get no added benefit. Okay? And just for a clarity PIE is a compiler flag, right? So I could have my code run PIE or not. ASLR is a kernel option, right? So keep in mind one's a userland thing, one's a kernel mitigation. Okay, and like then there's also KSLR, which is ASLR just for kernel programs, right? And you can randomize things on the kernel too. So like there's various levels to these things. Yep. So just as a recap, bypassing ASLR PIE, use printf, puts different things, delete addresses, return addresses, global variables, memory locations, and then abuse those in your payloads to get more information. Right? Usually, the thing you should take away from this mitigations class is one piece of information no longer solves the puzzle, right? If we want to exploit something, we need, maybe 3-4 memory leaks, buffer overflows, sometimes more stuff, maybe multiple buffer overflows because maybe your buffer is small, and it just makes things harder in life, which is good, except for my job, but it's good. It's a good thing, right? I recommend, because this will be project 3, I think, yeah. Project 3 has one GOT ROP. There's 2 ROPs.
No, the GOT ROP is project 4.
Oh, project 4? Okay. But regardless, you'll need to know about these mitigations for the midterm. The midterm is also less gamified. It's much more straightforward. We tell you the exploit you need to do, and you just need to have the raw skills to do it. There's no tricks or reversing heavily. But you should understand these mitigations, how to bypass them, so you can perform it the day of the midterm. If we haven't talked about it, the midterm is just a project, one challenge, one program. Basically, just do a full exploit chain, but you're 48 hours, right? You just gotta get it done in those 2 days. And this is like real world. You're hired to do a security audit or something, and they give you a week. And maybe it's a 1,000,000-line code base, and you have a week, so you just throw things at the wall and see what works. Okay, so one more defense mechanism right before class ends. So partial relocation, read only. Basically, this is just like, you remember how we change things on stack, so we can't override local variables? This is like the same concept, but with a global offset table. We just put global variables right after the global offset table. So if we had a buffer overflow in a global variable, it wouldn't override the offset table, right? Generally, because this doesn't really have any implications in terms of runtime, right? This is all compiler stuff. This is on everything. Full relocation is a little different. So I think we also do the change because that's just a compilation flag. But now, remember when I said we don't link everything at the start for runtime reasons? This forces linking every time at the start. And then the global offset table is no longer writable. So you can't do any write changes. So basically you trade startup times really bad, but there can't be a bug related to global offset table. You can still leak from it, you can still recommit, but it's no longer writable. You can't abuse it to redirect execution. And then another bug that's not on the slides is becoming increasingly popular in operating systems like Windows, and it's kind of like a modern day thing, so with ROP, we abuse the fact that we can reuse code, right? And we kind of just jump anywhere we want. So now, what operating systems like Windows are doing, I don't know any Linux version that's doing it, but we flag the start of every function saying this is a valid jump location, and everything else is not. So you can no longer jump halfway between functions, right? And this basically kills ROP unless you do a full function execute. It's a little bit more costly. Basically, every function call has another opcode or 2. But it really kills ROP, and that's starting to get implemented. Is there any other bugs I'm missing? Or defense?
Just right now you mentioned CT, or was that for CT?
It's like the same thing. CTI.
They're a bit different. Yeah.
But basically,
there's a few, especially Windows starting to implement a lot of hypervisor-based mitigations that, for example, make sure that in your kernel, it's completely impossible to have code that is executable and writable at the same time, and basically just killing off bug classes entirely with that.
Yeah. Stuff's getting really safe, which is a good thing. Pain in the ass, but it's good. Yeah, that's lecture.